Damn it. Okay. So calcium is 20 electrons. So if we're following the diagram on the left, you start at the top, which is 1s, and s holds 2 electrons, so I'm going to put a 2 there. 2 is not 20, so I'm not done, and I have to continue on. So the diagram on the left says after 1s, I go to 2s. S still holds 2. 2 plus 2 is 4. 4 is not 20, so I'm not done, and I have to continue on. The diagram tells me that after 2s, and I follow my little arrow here, I next go to 2p. P holds 6, so if I make that a 6, 2 plus 2 plus 6 is 10. It is still not 20, so I am not done, and I have to continue. The diagram says next after 2p is 3s. S still holds 2. 10 plus 2 is 12. I am still not done. The diagram does say that I loop back up and hit 3p. I'm still going to put 6. I was at 12. 12 plus 6 is 18. 18 is not 20. I have to continue. Now, it's after 3p that people get messed up if they don't follow the pattern correctly. After 3p, the diagram tells me to go down to 4s. I do not go across to 3d. So 4s, s can hold 2. I don't need it to hold 2 if I don't have to have 2. But I'm at 18 and I need 20, so I actually do need 2. And if you double check yourself and add 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 6 is 18, 18 plus 2 is 20. That is the correct configuration for calcium. Now that's doing it using the diagram on the left. Using the diagram on the right, you can say, okay, I need to put 20 electrons in this diagram, and I can put 2 electrons in each circle. So kind of the way to do it is be like, okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I get the same thing. It's just a different way of doing it. They're both completely valid. It kind of depends on what makes more sense to you. But looking at it this way, you count in drawing your slash marks in the diagram and then say, okay, so I used up 1s and I had 2 things in there, and 2s and I had 2 things in there. 2p, I had a total of 6 things in there. 3s, it was 2, and 3p, it was 6. And 4s, it was 2. And it's easy with the diagram on the right to see that you fill up 4s first because it's lower down in this diagram than the 3d or the 4p. If it's lower down, it fills up first. So that's kind of how that works. Are you with me before I move on to the next page?
I have a question.
Yes, ma'am.
So how do you, I'm just kind of like not understanding like the exponent change. So you start with like the 1s2 and then the 2s2. So on the 2p, why is it 6?
Because p has 3 orbitals or 3 circles, whereas s only has 2.
So you're multiplying the circles by 2.
Yes.
Okay.
Each circle can hold 2.
Okay.
So, I understood the left side, but not the right.
Okay, what about the right?
Like, what order did you just do?
Starting from the bottom. So, like, give me another element. Just pick another element and we'll do another one.
Sodium.
Sodium. Okay. So if I look up the atomic number for sodium, how many electrons does it have?
11.
11. So in the diagram on the right, if you're going to use the diagram on the right, you always start at the bottom because you start at 1, right? The diagram on the right is like dumping a cup full of electrons into a funnel, and they'll funnel down the diagram all the way to the bottom and fill up from there. So electron number 1, electron number 2, electron number 3, electron number 4, and then you have to follow the empty bus seat rule in this diagram. So electron number 5, electron number 6, electron number 7. Go back, because I have to have 2 marks in each circle. Electron number 8, electron number 9, electron number 10. I have 1 more electron, and that goes up here in 3s.
Oh, okay. So this
Okay.
is always the order?
Yes. That is
I
the
thought
nice
it
thing about electron configurations. The order never changes. Once you get used to the order, you'll just be able to rattle it off because it never changes.
Okay.
All right. 2s2, 2p6, 3s1. And if you add those exponents together, 2 plus 2 is 4, 4 plus 6 is 10, 10 plus 1 is 11, and that's where you get that. So there is a nice thing to remember. Elements with an odd atomic number, right? 11, 19, 41, all right? So if their atomic number is an odd number, they will have an odd number as the last exponent in the configuration. So that's a good mental check, because otherwise 2, 6, 10, and 14 are all even numbers. You're always going to write even numbers, except the very last number could be an odd number. So let me switch over to the next one, and we can do some of these together. So it says, write the electron configuration for the diagrams that already exist. So orbital box diagrams are annoying to do in a Word document, which is why it looks like this. So you can imagine that that's a circle, that's a circle, 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 right? Circle, circle. Those 3 are together, and then that's the 3s. So it's not that hard to look at, but then it's like that. So for this first one, you know, I already did it for you. You've got 2 in the 1s, so it's 1s2. 2 arrows in the 2s, so it's 2s2. And then you had 1, 2, 3, 4, 5 arrows in the next set of circles, which is 2p, so it was 2p5. So how do I know that this is fluorine? Well, you add up the exponents, that tells you the atomic number. Fluorine is atomic number 9. So the next one, if I were to write out the electron configuration for what's there, where do I start? What do I start writing?
One S2, 2S2, 2P6, and 3S1.
Yep. 1s2, 2s2, 2p6, and 3s1, because there are 1, 2 in that one, 1, 2 in that one, 1, 2, 3, 4, 5, 6 in that one, and 1 in that one. That's where she got those numbers. And if I add up those exponents, 2 plus 2 plus 6 plus 1 totals up to what?
11.
11.
Which is what element?
Sodium.
Sodium.
Sodium. All right, so the last one extends a little bit beyond that. So it starts in the same place because they all start in the same place. So rattle off, what is this third one going to be?
1s2, 2s2, 2p6, 3s2, 3p3.
3s2 and 3p3. And what does that total up to?
11 still? 15.
15.
I really can't do math.
That's okay. Morning. 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, 12 plus 3 is 15, which is which element?
Phosphorus.
Phosphorus. For us. Okay. So we need to practice some of these. So to make things easier, I'm gonna write down the number, the atomic number for each of these things, and then have you guys use your, and then I'll flip it back to the patterns on the previous page so you don't have to skip back and forth, so that you can practice writing these out. So I would like to point out number 1 and number 6. Magnesium and manganese. This is a common problem. Those two words are almost exactly the same, but they are not the same element. So magnesium is Mg and its atomic number 12. Manganese is Mn and is atomic number 25. So they are a little different. But magnesium is 12, fluorine is 9, argon is 18, lithium is 3, potassium is 19. Antimony is, I think,
Put 98 for argon.
51, I think. Silver, 47, unless I'm crazy. I might be. 36, rubidium, 37. If I got one of those wrong, let me know.
You put 98 for argon.
Oh, no, that's 18. I don't know what that is on my screen.
Oh, okay.
Yeah. Write it over here so it's easier. 18. Yeah, it's like some weird little oval that's there. Okay, so I will give you 5 minutes. Do them. Try them. If you don't understand something, throw a question up in the chat.
Miss Baskin,
Yes.
can you put the charts back up?
Yes. I just wanted to make sure everybody got that stuff. Cool.
Thank you.
Mm-hmm. Couple more minutes.
Hey, Miss Baskin.
Yes, Josh.
I'm sorry, I had left the room. What are we doing right now?
You are doing the practice on the last page, on the back page.
Okay.
Okay, so we're gonna switch back over and spot check some of these. The early ones are easy to do because they're short. The last ones, not so much, because they're long. Let me zoom in a little. Okay.
I thought Argon was 98. That's why I was
No,
texting.
sorry, that was some weird blip on my screen. It is 18. I don't know why it came up as 98. Okay, so we're going to rattle these off in cadence because it sounds kind of funny when we sound like we're chanting electron configurations, but they all start off in the same way, which makes them easy. So start off, let's speak out. What is the full configuration for magnesium?
1s2,
2
2s2,
2s2
3s6,
3s2.
Yeah, good.
And then it ends there, right? 1s2, 2s2, 2p6, 3s2. Okay, fluorine's up above, so we're gonna skip that one. You can check yourself up there. Argon with 18. We know it at least has magnesium's thing, right? So 1s2, 2s2, 2p6, 3s2, and then what does it do? 3p6, because you add 6 to 12 and you get 18 and it's done. Lithium, super short. 2s1. So this is actually the first one where you can see that last number This last number does not have to be 2, 6, 10, or 14. If it's the last number, it can be smaller than that because you don't want to overshoot what the configuration is. Potassium, tell me that one.
Wait, Miss
Um,
Beth.
Oh, yes?
So when you said that if the atomic number is odd, then the ending number has to be odd too, you mean the exponent?
Yes.
Okay,
Okay.
thank you.
Uh-huh. Potassium, so this is an odd number. Okay, what do we got?
1s2, 2s2, 2p6, 3s2, 3p7.
3s2, 3p, the what, huh?
7.
Can I have 7 in P?
I'm guessing.
No.
My biggest number I'm allowed to have in P is what?
6.
I'm
6.
6.
It is 6. So after you fill, you have one left. You are correct. Where does it go?
4s1.
4s1.
Okay.
Okay. So, yeah, you can't go over that, and then it bumps into that next one. Let's do manganese.
1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5.
Yes, 4s2, and then 3d5. Because I only need 5. If I had written 3d10, I would have way too many electrons. I only need 5 in that last spot, so it does do that. So let me point out, I'm going from, it's like real normal until it's not. 1, and then 2, and then 3, and then 4, and back to 3. Yes, that's the correct order. So just follow along. That is the correct order. Now for these last ones, I'm not going to write all of them out because that takes a lot of space and a lot of time. But if you did it right, what is the last thing you should write for antimony? What does it end in?
5p3.
5p3. What does silver end in?
49.
49.
In my mind, it's her. So
49. Krypton ends in
4p6.
4p6. And rubidium ends in
5s.
5s1.
5s1. Okay. Now, part of the reason why I'm not writing those full things out is because once you get to bigger elements, it's really super annoying to write out the full electron configuration. So there's a shortcut. That's what your video for this week is on, and that's what the other packet picks up with. So I know there's still some stuff down at the bottom, but we're done with this thing. So right now, I'm going to switch over to my periodic table, which I have the benefit of constantly using pretty clean periodic tables because I'm using it as a PDF file. So on this thing, you can use the periodic table actually to write an electron configuration, either a long one or what we're going to call a core notation, a short form one. So somebody yell out one of the high number electron or high number elements that you see here on this periodic table.
Berkelium.
Berkelium. All right. This guy. Whoops. Okay. So that's 97. And if I had to follow that diagram to write out an electron configuration of 97 electrons, that would be super annoying to have to constantly remember that. But I don't have to do that because my electron configuration is the periodic table. So I want to point out that S can hold 2 electrons, and we refer to these 2 columns over here as the S block, 1, 2. D can hold 10 electrons, and if I count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, this middle section is what we refer to as the D block. P can hold 6, and if I look at this section at the right, 1, 2, 3, 4, 5, 6, it's my P block, which by default leaves my bottom as the F block. You have period numbers that are down here off to the side, and the period numbers are the large numbers in the electron configuration for S and for P. So if I look at my periodic table and I'm trying to get to berkelium, I start at the top and scan my way left to right. And I would say, okay, so those two tell me to start with 1s2. And then I would go these two, and that would be 2s2, 2p6, 3s2, 3p6, 4s2. When I jump into D, I have to remember that my number goes down. So 3d10, and then I cross over into 4p6. And then I start in on row 5, 5s2, drop down when I do D, 4d10, cross back over here, 5p6, 6s2. And then there's a lot of disagreement about what kind of happens here, but essentially you go down and you fill up these, 4f14, and then come back up here and do 5d10, 6p6. My God, I'm still not done. 7s2. And then I would fill in and come all the way over to here and end in 5f. And if I remember correctly, that would be 9. Now, that's a lot. But that's how anybody who does this a lot, that's how you look at the periodic table and just do electron configurations. Now, I don't want to write all of that at all. So the other thing you can do, and this is what I'm about to teach you, is I can say, okay, I can put all of that in a pair of brackets. And I can use this element and say that actually that thing is brackets radon 7s2 5f9. And that is a lot shorter to write because that brackets around radon is saying that this is storing 86 electrons. So what I'm going to show you how to do is to use the noble gases to write a shortcut of configuration. So now you can switch over to this guy, advanced electron arrangement topics. So this is where we're going to go in today. I'm going to show you some of this stuff. We are not going to finish this packet. We'll finish it on Thursday. So to do what we refer to as core notation, and core meaning putting the brackets, right? That's what we mean by core. You must start with a noble gas in brackets. So that's the thing about core notation, is it has to be noble gases. You can't just pick whatever element you want to do. That's not a thing. You have to pick a noble gas. The reason why we pick a noble gas is because those are the ones that are all filled up, all right? Because these are filled up, right? So we are talking about these elements, right? That's where you can go. That's what your core configuration can start off with. Now, this is a way to store electrons. So you are storing electrons in those brackets to say, I'm going to cheat and start off by saying, well, if I started off with helium, I'd be storing 2. And if I started off with neon, I'd be storing the first 10, the first 18, the first 36, the first 54, the first, 86? Let me start losing count. 54, yeah, 86, or 118, which you're not going to use. So you get to store that many. That drastically reduces the length of your configuration that you have to write. But if you think of the periodic table as your electron configuration, the very next thing after one of these noble gases, when you come back over, is an S, and the energy level is going to be the period below the noble gas. Right? Because these are, right? These period numbers correspond to the S. So if I started off my configuration with neon over here, my next thing I would write would be 3S. So this would be, right, 3S, 4S, 5S, 6S, 7S. We wrote in here 3D, 4D, 5D, 6D. These are my P's, so 2P, 3P, 4P, 5P, 6P, 7P. And then these are the 4F and the 5F, recognizing that you go there and then you go there.
Oh.
Okay. And then the F's pop back up to the D's. We don't normally ask about like high number elements. Most of the time we're dealing with elements in the first 5 periods. So that's still some big numbers, but it's not like getting into an insane sort of stuff. Okay, so I think I can demonstrate this a little bit in these practice problems. Okay, so we did argon's configuration on the other page, and we said it was 1s2, 2s2, 2p6, 3s2, 3p6, right? Because I'm looking for 18. But if I look at this and I say, okay, I've got 18. If I want to condense it, I need to use a noble gas that is smaller than the number 18. So which noble gas is smaller than 18?
Neon.
Neon. So I can write neon in brackets. That neon in brackets is storing my first 10 electrons. Neon is right here. So if I look, the next thing after neon is going to be 3s. So the rest of my configuration would then pick up there 3s2, 3p6. So I have essentially stored that part of the configuration in these brackets.
So you can only store with like is there only, will you only be using one, like just neon, and then you continue?
Correct.
Or like, okay,
Yeah.
so you only use one element
Yes.
for the brackets.
And
Okay.
it has to be one of these noble gases, 2, 10, 18, 36, or 54.
Okay, I get it.
Okay. So magnesium, we had written before, was 1s2, 2s2, 2p6, 3s2. It's 12. What noble gas is smaller than 12?
The neon.
The neon again. So neon is storing 10. So how many do I have after that?
2.
Only 2 left. And if I look at it here, it's storing all of those, and all that's left is the 3s2. Now, neon and nitrogen and lithium, well, they're even smaller. And most people wouldn't use this core notation for elements as small as nitrogen and lithium. But if we were just going to write the core notation, what noble gas is smaller than 7?
Helium.
Helium. So I could put helium here. That stores only 2 electrons, but it's something. But looking at my periodic table, if I start here at lithium, what is the next thing I would write?
2s2.
You'd start here. You'd look at the period in the row below the noble gas you look at. So if I started with helium, the next thing down is 2s. And I would say, okay, I have to pass through 2s. That's two things. And then I would go into 2p, and it would be 2p 3, because 2 plus 2 is 4, 4 plus 3 is 7. So then if I'm looking at phosphorus and chlorine, phosphorus is 15 and chlorine is 17. So what noble gas should both of those start with?
Neon.
Neon. Even though chlorine is right next to argon, you can't start with argon because argon already has more electrons than neon, more electrons than chlorine is trying to have. So that doesn't work. So both of these are starting off by storing 10 electrons there. Looking at my periodic table, if I'm starting here at neon and I scan over, my next thing I'm going to write has to be 3s. And they would both be 3s2 because they are more than 12. So 10 plus 2 is 12. And after 3s, my periodic table says I bump over into 3p. And how many do I need to have for phosphorus in p?
3.
3. And how many do I need to have in p for chlorine?
5.
5. Now let me show you how you can very easily cheat that on the periodic table. Come on. Okay. So if I look at all of this, that's phosphorus. So not only is phosphorus in the third row in this P block, so I know it's going to end in 3P something, but it's in the 1, 2, third column, so it's going to end in 3P3. So it's really easy to kind of use the periodic table as a grid system to go along with your electron configurations. So before I end class really fast, let me show you one more just straight off the periodic table of doing something. So for instance, oops, forget it. If I wanted to do 10, what noble gas would I start with if I want to do the electron configuration for 10?
Krypton.
You'd start with krypton because it's the noble gas before it. So for this guy, I would say, okay, so I'm going to start with krypton. And then I look at my periodic table and say from krypton, I look over, what is the next thing? 5 here. So that's going to be 5s. And I passed through both columns there, so it's 5s2. And then I continue having to go through all of this. After 5s, I have to remember that crossing over into the D block drops my number down. So 4D10. And then I cross back into the P block and I'm in the second column. So 5P2. And if I add up those exponents, remembering that krypton is storing 36, so 36 plus 2 is 38, plus 10 is 48, 48 plus 2 is 50, and that's my atomic number. So here's what I will say. The College Board and I do not care which method of configuration you use. You can use the long form or the short form. It does not matter. They tell the same information. So if you are more comfortable counting up electrons on this guy Cool. Then you can do electron configurations and you're fine. If you want to try and continue to practice doing the core notations, cool. It is shorter and it does help you see the periodic table in a different way, but they are the exact same thing, just so you know. Okay, so there's that. So let me switch back over so we can wrap things up and I can let you go. Okay. Yep. Nope, we did that. The shortcut. Cool. Okay. So now let me talk specifically about term 4, because I've got 30 or 40 people in here, so that's good. So if you actually read my emails and you read the stuff in Google Classroom, you already know this, but just saying it out loud again, you start term 4 with a blank slate. You have no grades. That makes it decidedly different than term 3 when you had grades. So since you have no grades right now, you have to do work in term 4. You have to give me something. You have to give all of your teachers something to be able to build a grade. But they have changed what that is. It is now 50% participation and 50% practice and application. That is a huge increase for the participation. Practice and application stayed the same, and we have thrown assessments out the window, which means no teacher in any of your classes should be giving you anything called a quiz or a test. So there's that. For me and my class, because we were given flexibility on what we considered these things to be, for me, participation is going to count as the following: doing an ed puzzle and filling out exit tickets at the end of my classes, whether you are here live in class or you watch it on YouTube. I will give you a bit.ly link for a exit ticket that you have to fill out. Now, why am I doing it this way? Because the district is mandating that each teacher have 3 points of contact with a student across the week that you can document. Ed puzzle documents when you fill out an ed puzzle, and the exit tickets are time-stamped. So I have an electronic record of me actually interacting with you. So do I keep a hand record of who shows up to these classes? Yes, I do. Will that stand up as much as a time-stamped electronic ticket? No. So I'm going to have electronic tickets to be able to prove that we have interacted so that you have proof of your grade.
Wait, so Ms. Baskin, for
Yeah.
the exit tickets, are you going to give us a link?
Yes.
So you're going to send out a link through your Remind, and then we're just going to click on that, and where you just fill out whatever it is, and it submits it to you through there?
Okay, so I'm not going to do it through Remind. It's actually on a slide here, and I'm going to drop it in the chat. And then for people who are either currently watching this on video or, you know, something like that, if you in the future are unable to make a class and you watch this through video, in the description underneath the YouTube video, there will be a link for an exit ticket. But yes, it will, once you fill it out, it will submit it and I'll have that. So we may have a few kinks here at the beginning as we start it, but it should be fine. So
Ms.
that's
Baskin?
participation.
Oh,
Yes, ma'am.
fine.
Okay.
I was going to ask.
Uh-huh.
Go ahead.
Oh, I was just going to say, participation should be the easy, low-hanging fruit, right? I'm giving you, if you can't be in class live, you can still watch it on YouTube. You can still technically interact and prove to me that you watched the lesson and get all of your points. Like, there is literally no reason for people not to get all 100 points in participation, because I made it real easy.
Got you.
Cool.
Mr. Baskin?
Yes,
I'm sorry.
Jameer.
Is the exit ticket graded on accuracy?
No part of participation is graded on accuracy because that's why it's participation.
Okay.
Okay. So practice and application. What I'm doing, because I know people are in various different places, I'm giving you 2 things for practice and application every week. One of them is a completion grade. You do it to whatever level and it's full credit. The other one is actually graded for accuracy. What that looks like this week is in Google Classroom, under the practice and application assignment, I had 2 links. One was for a practice website for you to be able to practice electron configurations, but there's no like account or anything like that to do. So all I'm asking is, after you practice on that website, take a screenshot and upload it to the assignment in Google Classroom to prove to me that you actually practiced on that website. Cool. There's half of your practice and application points. The other check of points is going to be, most of the time, probably a quiz. All of my quizzes is, you will have 3 attempts to do it. You shouldn't do it until you actually know what you're doing. Because that is the one assignment every week out of everything that will actually count for accuracy. But
Ms. Baskin,
you have 3 attempts to do it. Yes.
so didn't DCPS say that we're only supposed to get 2 assignments a week, and one of the assignments is extra credit and the other one isn't?
No.
Because that's what they told some schools.
So we only have the 2 grade categories: participation and practice and application. We can
Because I
only
saw a
have,
document where that's what they said.
well, it's not quite. So there's 2 grade categories: participation, practice, and application. We can only have 1 grade in each of those things each week. And then in addition, there is extra credit, but the extra credit is part of practice and application. So technically, there are 3, if you go into Aspen right now, you have 3 grades listed for this week. You have a week 1 participation, you have a week 1 practice and application, and you have a week 1 extra credit.
Because I thought that you were supposed to have the same amount of extra credit grades as you do graded grades. Like, it's supposed to be equal.
It's supposed to be equal within the practice and application category.
Okay.
So what you'll see is that participation is listed as a P. The practice and application and the extra credit are both listed as PA.
Okay.
So because it's the practice and application, because participation is not supposed to have anything at all to do with accuracy at all. But practice and application is, and so that's where the extra credit is, because that's where it's going to go to help boost grades.
Okay.
Okay.
Ms. Baskin.
All right. Who? What?
You can go first, whoever said Ms. Baskin.
So Dr. Nickerson was saying that, like, it's kind of pass or fail for this quarter, or not pass or fail, but like something like that. Like, what was it?
It's grade neutral.
Okay.
So here's how it works. I know what your grades for your 3 terms are. I know what the average of those 3 term grades are. If your term 4 grade is lower than that average, your term 4 grade will not bring down your average. If your term 4 grade is higher than the average of your 3 terms, then it will pull up your average. So in general, what term 4 does is it cannot bring down your course grade, but it can bring up your course grade. And let me say that since that happened, it changed the course grade calculation formula, but so I had to recalculate what I predict course grades will be. This was actually a great thing for people, because it means even though some of my lovely individuals who are in this classroom may not have had some stellar grades, some advisory, I can say that 100% of honors chemistry students have passed for the year. Everybody. Regardless of what you got any term, I can say with 100% clarity that every single person has passed based on what you have done in the first 3 terms. So that being said, this is an easy opportunity to bring your grade up. The other thing I would say is those people who are planning on taking AP chemistry, you kind of need to know how to do this stuff we're doing here at the end of the year, and I'm sorry.
Miss Baskin, is that kind of how what they were talking about in the email? Like, if you had a bad grade before quarantine, everything we did during quarantine was just extra credit, but I never understood all that. So it's like
basically,
did it count?
the stuff in term 3 could only bring up your grade.
Okay.
Yeah.
Because it was saying it was like a pass or fail thing. Was that about
That was about overall grades. That's different.
Oh, okay. So the grades that we finished off with in terms they actually count, right?
Yes, absolutely.
Okay.
Yeah, because they should have been the same as of March 16th. They should have either been the same or higher than what they were.
Yay.
Okay, so quick review of what is now due on Sunday, because I have shifted my due dates because they want things done by week. So fine, things are going to open on Monday mornings and they're going to close Sunday nights. So that core notation ed puzzle video, which I technically assigned last week, nope, everybody got an extension through Sunday of this week. Okay, so you need to do the ed puzzle, which a lot of people have already done. I'm about to give you the exit ticket, which you're going to have to fill out. You need to do the Electron Configuration concept builder and upload a picture that has your name on it, which there's a space for it when you do the concept builder, and upload that to the classroom assignment. Several people have already done this, so if you have questions about that, ask me, but the link to that is on Google Classroom, and then you need to do the quizzes, and that's it. So all of those things, we are done with submitting paper assignments. And then if you want to try the free response questions, you can. That's how I'm doing extra credit.
Does it matter when the exit ticket is turned in?
No, as long as it's through Sunday. Because I know some people aren't going to be able to watch, like the 10 people who aren't on this right now may not be able to watch it today, so that's fine. So that's the exit ticket. Okay, I'm going to type it into the chat too.
How are you gonna send it in Remind?
Oh.
And it's short, so you just click on that. There you go. And that's it. So unless you've got any questions, that's it for class, and I'll see you on Thursday.
Thank you, Ms. Baskin.
Mm-hmm.
Thank you, Miss Baskin. Have a good day.
Thanks.
Thank you. Have a nice day.
I
have a question.
Yes, ma'am.
So for lanthanum and actinium, they look like they're in the D block, but you wouldn't go to the D block before going to the F block. So how would you write that?
This is why we normally avoid elements in that area, because there's actually disagreement about the order in which the electrons fill. Some people think they actually do fill 5D1 before going to 4F, and some people don't. The truth is, kind of once you get to an element that's literally that big, the energy levels and sublevels are so close that there's not actually a huge difference. So you get electrons fluctuating back and forth between the Ds and the Fs, which actually makes for really interesting chemistry. And it's why a lot of those elements down there, especially in 4F, the lanthanides, those are the ones that we use in electronics because they have interesting magnetic properties because of their electrons. So yeah, but that is a realm of we're not sure what happens. So we don't actually ask questions about them.
Okay.
Yep.
Have a good day.
Thanks, you too. Davi, you, Annabelle, Lena, you got any questions? You good?